Today I'll be talking about a new data assimilation scheme that can work for general state space models, um, specifically for nonlinear and non-Gaussian models in high dimensions. So this is a joint work with some collaborators from different institutes. I'll start by introducing the state space model. So as we know, state space model consists of two things, the dynamical model and the observations. So the dynamical model here is a continuous time stochastic process, ZT, for t greater than or equal to 0, and each ZT belongs to RD, so it lives in the D dimensions. And the data is a sequence of noisy observations at times tk, k greater than or equal 1. So it's at discrete times t1, t2, up to whatever. And each of these data vectors belongs to RSMK, where MK is the number of the observational locations, for example, on a 2D grid. And S is the number of variables that are observed per every observational location. And so we set dyk to be S times mk. And in general, the space of the data is less than the space of the hidden signal. In addition, and that's why this method was developed for this problem, is that we assume that the locations of these observations, which are xtk1 up to xtk mk at time k, these are random, so they are not certain. And we assume that these locations are a function of the hidden state that we are trying to infer. So it's given through this integral here, where h is some function of the hidden state zs. And the goal is to find the filter distribution or to estimate it. And the filter distribution is the probability of the state at time t, given all the observations at the discrete time instances tks up to time t. So as an example of a hidden state is the following. So it's a PDE with discrete time additive spatial noise. So consider a 2D grid G. Then ZT will be a vector containing the variables at positions defined in this grid. And when we don't observe, the state is given as a solution of the PDE at time t, but we running the PDE from time tk minus 1 up to t with initial conditions ztk minus 1. And at the time of observation, it's the same thing, except that we add noise WTK. For example, it could be Gaussian noise sampled from this Gaussian distribution with a covariance matrix QK. As an example of an observational model where the locations of the observers are unknown or random is the following. So, for example, at time tk, we have ND observers or drifters, for example, in the ocean, in a specific region of the ocean. And these drifters, they observe the water's horizontal velocities u and v. Now, these drifters, they actually move with the water. So they move with according to the hidden signal they're trying to infer, and therefore their positions are random. So in this example, we have three drifters, as we see in the picture, and each of them observe the u and the v at their location. And so we have the space of the observations is 6, so 3 drifters times 2 variables, and the dimension of the state space model is the number of grid points, which is 29 times 11, times the number of variables per each grid point, which are 3, the h, u, and v, the height, velocities, and the x and y, which equal 957. As for the observational model, as an example, what one can take it to be as follows. So YTK is some map a function applied on the state ZTK plus some Gaussian noise with covariance matrix RK. Now, we assume the following. So we need to have a transition density, and also we need to have a likelihood density. So the probability of finding ZTK in A, where A is subset of RD, given the previous state at time k minus 1, is equal to the integral over A of some transition density F k that takes ZTK minus 1 to ZTK. And also assume that the probability of finding the observations in a set B, subset of R dyk, given all the state variables up to time t, and also all the unknown locations, xt, and the data up to time tk minus 1. This is to be an integral over B of the likelihood density, which is written as capital GK, and it includes the random location XTK. Now, in other state space models, when we know where the observations are, we don't have to include this XTK in the likelihood, and so we write it as a small g GK. So it's known that the filter density can be obtained recursively by integrating the so-called smoothing distribution to have the following formula. So the filter density is pi k of ZTK, and we drop the dependence on the data. Is just the likelihood times the integral of the transition density times the filter density at the previous time step k minus 1. So because the locations, the unknown locations of the observations depend on the hidden signal, this generates a long range dependence, and this makes this model very challenging. And so it's a barrier to using, for example, some particle filters that have been developed for high dimensional problems. So we tried different methods, and they all failed to simulate such a model. And the issue with the particle filter, for example, and I mean the variants of the particle filter, like the ones that you tempering or nudging or whatever, that they suffer from the path degeneracy or the weight degeneracy because of the resampling steps. You need to do a lot of tempering for this model, and so to avoid that, we aim to use different methods where we don't have any weights, and so we don't have this issue of weight degeneracy. And one way is to use MCMC to sample from these distributions. However, this integral here makes it difficult, and so we estimate pi k minus 1 as follows. So the algorithm starts at T1. So the first time you observe, it's just you have this nice filter density, and so you can use MCMC to sample from it. No integrals here. So you run the MCMC, for example, random walk metropolis for n plus some n burn steps to generate n samples from this filter distribution. But then at later observation times, tk, k is greater than or equal to 2, we replace this pi k minus 1, the filter distribution at the previous time, by an empirical density, which is 1 over n, the sum of the delta measures centered at the samples ztk minus 1 of I, which are the samples obtained from MCMC at the previous time step. And when you put this here, then this integral collapses to a sum, and then you have this formula. However, the issue here now, if you want to sample using MCMC, then you have to calculate this density n times. And so you need to run n steps of MCMC, and you have to, in each step, you have to compute n calculations of f. That makes the cost n square times the cost of computing f and plus the cost of computing j. And so this is it's too much, and so we instead sample from the marginal of the joint distribution. Sorry, we sample from the joint distribution, this distribution here, which is a distribution in the state ztk and some random integer between 1 and n, which is the same as before, except here there's no summation, and you have the probability of the uniform probability of j on this set of integers. And why I'm saying this is a marginal of this, if you take the summation over j, then you go back to this to the original distribution, the approximation here. Then you run MCMC to sample this pair from 1.1 initialized at some random sample from the previous time step. The cost of this algorithm, it ranges from n times d, where so you n samples in the MCMC times the cost of computing f, and the cost of computing f depends on the structure of the covariance matrix in the background. So if it's, for example, diagonal, then the cost will be n times d. If it's a full structure, full dense matrix, then the cost will be nd squared.
You have 3 minutes left.
Sorry. Then one runs one runs this algorithm m times in parallel and takes the average of these runs. And this result is assures the convergence of this method. So this algorithm is optimal, like particle filter. So as n goes to infinity, then the LP error will be 0. Now, as I said before, the algorithm was designed for when the observation locations are unknown or random. So, and we assume that each observer location is a function of z, the state, the hidden state. So we can approximate this integral by using Euler's scheme. But then the issue is that we have n paths of the states, because we or n particles here in z, so we have to do another approximation. We take the average over these particles to have this estimation of the location of the observer. And then in the previous algorithm, we just replaced the likelihood density small g with the capital G that takes into account this X bar. I just show some examples. So we start with the a very simple example, which is a linear model, but in high dimensions, and we compare against the ENKF in simple transform Kalman filter, error subspace transform Kalman filter. And since we know the truth, which is computed through Kalman filter, it's easy to compare these methods. So we run it, we run these, and then we record the machine time once 70% of all the errors, which are defined as the difference between the mean of the Kalman filter and the means of the filter of interest at every time step n, at every state variable I. So you have a matrix of size t times d, where t is the number of time steps. So if you have 70% of these errors less than sigma y over 2, which is the sigma y is the standard deviation and then in the data noise error. So once 70% of these errors are less than sigma y over 2, we record the time. And here, for example, I plot the time versus the state dimension. So I keep increasing the dimensions starting from 2000 up to 16,000 dimensions. And we can see that the SMCMC, for example, at dimension 16,000, it takes 10,000 seconds to get 70% of the errors less than or equal sigma y over 2, while the other methods, for example, the ETKF took about 6,000 or 7,000 seconds. It's a huge jump. And the other figure here, I fixed the ensemble size to be 1,000. And I choose this number because I want 50% of the errors to be less than or equal sigma y over 2. So 1,000 for all the methods. In this figure here, the left, the number of ensemble is not fixed, but here it's fixed. Still, SMCMC is the cost is much lower for a given accuracy. And as we can see from the table here, at dimension 16,000 for this example, for example, ESTKF is 8 times slower than SMCMC. ETKF is almost 7.8 times slower, and ENKF 4.5 times slower than SMCMC. The second example is the rotating shallow water model, and now we have unknown observation locations. Actually, we have drifters, and these drifters are obtained, their locations and the error is obtained from the National Oceanic Atmospheric Administration, NOAA. And the bathymetry and the velocities and elevation of the free surface, the initial conditions and also the boundary conditions are obtained from Copernicus Marine Services. And so we run this model on a specific region of the Atlantic Ocean. And we add a specific noise to the model such that this noise is zero at the boundary, because we don't want to have any noise on the boundary, because we have real data boundary conditions. And so it's structured like this. The observational model, as I said before, but now after we compute or estimate the location of each observer, given an X bar, we map it to the nearest surrounding grid node, and that's because we are dealing with a discretized model, and so we don't have continuous tracks, and so we map, for example, the location here to T1 and this to T2 and this to T3.
Could you please wrap up your talk?
Yeah. So this model was done on a grid 121 times 121, and so because we have 3 variables, the height of the water, velocities UMV, the dimension was 43,000, and we run the simulations for 33 hours, where we observe every 10 time steps, which each time step is 60 seconds, so every 600 seconds. And we set the number of samples in the MCMC to be 1,200. And this is a snapshot of the simulation. So U prior here is because we have real data, we don't know the reference, so we just run the forward model 50 times and we took the average and call it prior, and then we compare the filter against the prior, and these are the errors. Currently, I'm working on making a localization scheme for this model where I reduce the dimensions from D to D prime, and D prime is much less than D, and this localization is done through some approximation of the noise, the state noise covariance matrix. Finally, I have to say that this paper I'm presenting is published in Quarterly Journal of Royal Meteorological Society and can be found on this link here. Thanks for listening.
Thanks for the very interesting talk. I would, so there are two questions in the UPad. I will read one and please be quick in the answer. So there's one question by Philip Grievank. Can this approach be applied to remote sensing observations for which the signal location is not known? For example,
Yes.
a satellite observation of cloud top with an uncertain cloud top height. Right.
Yes, exactly. Yeah, it can, yes.
Okay,
It can
great.
be. Yeah, it can be applied to any general state space model, even if the locations are known as well.
Great, thanks.
For example, in the linear model here, because we know the location.
Okay, there's another question by Lars Nerger. Please just write the answer in the UPad.